So in this video, we're going to introduce the case of unsymmetrical bending of beams. So we're going to identify in what cases you're going to use the techniques that we're going to cover during the next set of videos for lecture 21. So in the case where we have symmetric bending, so we have symmetrical cross section and symmetrical loading about the neutral axes. It looks something like this, where we have a cantilever beam, where we have our x, y, and our z coordinates, right? And we have two bending moments that occur about our neutral axis here, where the stress about the neutral axis would be, due to those bending stresses, would be equal to 0. So the stress due to the moment mz would be 0 along the horizontal neutral axis, and then the stress due to the applied stress along the y-axis would be equal to 0 along the neutral axis that's going along the vertical direction. So, um, so, so we can define that symmetric bending will occur when the y and z axes are the principal axes, and this occurs when the mixed moment of inertia here is equal to 0. All right. So in the case for symmetric, when we have symmetric problems, our stress along the x direction or along the axis of our beam would be equal to this equation here, which is just equal to my over iz, or myz over iy. So in today's lecture, we're going to focus on two cases. The first case is if you have the cross area, sectional area is symmetric about one axis, but the applied load does not act within that plane of symmetry. So for example, if you had like a channel section, right, and we had a load that was about this axis here, that would cause this beam to twist. So like this. Okay, so that um, that would cause a different loading situation from our traditional loading situation, and would not give us the valid stress state. The second case is that if your cross-sectional area does not have a line of symmetry. So what that looks like is something like a Z or an S cross-section here. Okay, so so no matter how you load this section, it's going to have asymmetric properties. So we're going to focus on these two cases. The question I often get with these types of problems is, why would you use, if these materials or these sections don't behave symmetrically, why would you use them in your design? So one of the reasons you'd use them is that they're very, though they are maybe a little bit more challenging to design with, they do allow for some useful properties. So for example, if we have a U-channel section like this, right, and we compare it versus like a traditional like I-beam, right, if we have to ship, if we need to use, let's say for a project you needed 10 of these, 10 of each, it's a lot easier to stack and to ship 10 beams that fit within one another, like this, right, etc. Versus for the I-beams, you can only really just stack them up, depending on the sizes of their sections, you really can only just stack them up on top of each other. Sorry, cutting off here, but that's essentially you're going to save a lot of space here versus here. So if you have to transport materials to maybe a far location, etc. You can save a lot of space if you use asymmetric sections, and you could also, if you think about it that way, you can also save a lot on transportation cost.